guys. Okay, so I'm actually at school today then, so a little bit clearer video. Sorry about the last one. We are starting in on the second half of 1.3. So this is 1.3 part 2. So you should have already done the homework for the first half of the first half of 1.3, so part 1. So now we're moving on to different factoring techniques. So we've dealt with difference of squares, being able to factor just a normal, sorry, it's like flashing, I don't know. Let me try to turn this light off. Okay, not sure why it's kind of being weird. Okay. So yeah, we've done difference of squares and factoring a normal trinomial. So now we're gonna move on to factoring when it's a perfect square trinomial. So in factoring, sometimes we have kind of these formulas to help us out. So basically what this is saying is if you can come across, oh, I did not mean to write this part here. Let me erase that. If you can ever come across a trinomial where your first term is squared and the last term is a perfect square, okay, that's something like 36, 25, anything that you can cleanly take the square root of it, it's called a perfect square, right? So this would be things like 6 squared, 5 squared, 4 squared, 2 squared, any of those kinds of numbers. Again, just like the difference of squares, you're likely not going to see them already in that perfect square form. So it may not be written as 6 squared. It's going to be written as 36. And it's your job to know, oh, I know what the square root of that is. That's a clean square root. So we have two different forms. And the easiest way to kind of explain these two different formulas is just simply by seeing them. So we're going to start with the first example. Where did I set that paper down at? Okay, our first example is going to be d squared plus 12d plus 36. So let's pay attention to the signs here. Okay, paying attention to those signs, I can see I have a plus and a plus. In my two formulas, this top one is the one that has both addition happening. Okay, so I'm not going to pay attention to the second one. I'm working with this first one here. So I need to make what I have look like the formula I'm given. So this first part's already done, right? I have a d squared out in front. So my variables being squared, that's already set up for me. But my 36 in the back here, I do know that 36 has an even clean square root. So I'm able to take the square root of 36. But it's my job to write that as a number squared. I don't want it to be 36. I want it to be whatever number it is that squares to get 36. So the square root of 36 equals 6, okay? So instead of writing this as 36, I can instead write this as 6 squared, okay? We're getting down to it. We're almost in that same form. Things I can check off. I have my d squared, right? I have that squared thing out in front. For b squared, I have this 6 squared out in back. So now what I need to work with is this middle chunk, right? My middle is not written as it needs to be. I need to have my a times my b. So let's identify right now. My a, the one very first square, is d. So then my b, very last thing squared, is 6. So I need to have this so that it's 2 times a times b. So does that work out? Let's do this off to the side. If I had the number 2 multiplied by my a, which is d, times my b, which is 6. If I worked that out, does it all come to be actually 12d, right? This is like the determining factor, can I use this? So d times 6 is going to be 6d, still times 2. 2 times 6d is going to give me 12d. That was what I had in the middle, so this is just a different way of writing it, right? So since they're equivalent, that means that I'm able to write this in the form that I need to. So what I'm seeing right here is matching up to this form up top, okay? So I've done all the tests to get me to this point. I'm able to use this perfect square trinomial factorization. So now, since I was able to get this to match this part, now I can fill in my factored form, okay? This is the unfactored form, this is the factored form. So once I can get this to match up with what I have, I can now fill in the blanks. My A is D, my B is 6. So using that formula, I have to start with my A. D plus my B is 6. This is all quantity squared. All right. This is my factored form. Okay, so all of this was testing, can I use it? Can I use it? Am I able to use the perfect square trinomial factorization? This proved that I could. I used my A and my B in this formula to get my factored result. Okay, let's do another one really quick. If you don't want to watch one more example, you're more than welcome to skip ahead. I think all of my markers are just dying on me. All right, this example is z squared minus 26z plus, yeah, you can't see that very well. Let me try a different color. Plus 169. There we go, that's better. So when we're using perfect square trinomials or anything that says a difference of squares, perfect square trinomial, when you have square numbers, they get relatively large pretty quickly. So seeing something as large as 169 is not going to be uncommon for us. You're able to find square roots in your calculator, so I'm confident you'll be able to do all these. First thing I need to check, my very front number is in fact something squared, right? Some variable squared. So that part's good, that checks out. Now I need to see, is my last number in a clean square root? So it's ending in a whole number, no decimals. So I take the square root of 169. If you do that in your calculator, you'll go ahead and find that that is, or in your head, whichever one, you'll find that that is 13, okay? So I can also now rewrite this as z squared minus 26z plus, instead of 169, I'm going to write this as the value of 13 squared because this is equivalent to that, right? I'm not changing the value of this expression at all. I'm just altering the way that it looks. I'm modifying it. I am not changing the value at all though, because 13 squared is still 169. So I'm almost there. I can identify that what I have right now for my A, this front letter out here, is Z. What I have for my B value is 13. Okay, I'm going to have some people ask me, well, shouldn't it be Z squared or 13 squared? The answer is no, because it is A that's being squared, right? B that's being squared. So I don't take that squared with it. All I want to know is what's my A value and what's my B value, not that quantity squared. So let's test something. I need to have 2 times A times B in the middle. If that in fact works out, then we're going to go ahead and be able to use this. So I have to take 2 times the value of my A times my B, which is Z times 13. That gives me 13Z. Okay, now if I go ahead and distribute that 2 times 13 is 26, giving me 26Z. That is what I have in the middle, so we're good. I can go ahead and write this out as minus 2 times 13Z plus 13 squared. So again, this statement is equivalent to this expression, it's equivalent to this expression. All of these are equivalent, just written in different forms. So if I go ahead and use now my equation for a perfect square trinomial, I'm going to determine which one of these am I able to use. So looking at my operations, I have a subtraction and then an addition. This one has two additions, this version has a subtraction and then an addition. So I'm going to be using this bottom one this time. So I take my A value, which is Z, and I subtract it from my B value, which is 13, and then write that quantity squared. So the full factored out version is going to be Z minus 13 quantity squared. You should always end with something maybe more compact or more clean looking than what I started with. So that is perfect square trinomials. Kind of the same thought process as dealing with differences of squares, just a little bit different. Okay, so some people start to ask, like, why do we even want to factor? What's the advantage of factoring? There's a lot. One in particular is factoring allows you to find the zeros of functions, okay? So this is something called the zero product property. Basically what this tells me is literally that it is where the zeros of the function are. So again, some people might still be like, okay, put this in English, Ms. Nordman, I still don't know what you're talking about. When we're finding zeros of a function, this is basically going to be our x-intercepts. These are important for a million different reasons. When we're graphing, they're important. One huge thing on the SAT is they ask time and time again, find all the zeros of the functions. Now you can do this in many different ways, and like when we start to get into chapter 2, we'll find even some more difficult ways, but we'd rather do something easier. Factoring is always going to be the easiest way to find our zeros of the function if we're not graphing it. And even when we do graph it, we still like to use the zero product property to find those zeros that we don't have to do an XY table. So we're going to do an example then, using the zero product property in factoring to find the zeros of a function. Okay, so your directions would literally be find the zeros of the function. Okay, and we're calling these zeros because along my x-axis, my y value is going to be 0. So when we say these all are the zeros of the function, it's where I'm hitting 0 on that y-axis. Okay, so I'm crossing the x-axis at these points. I'm going to give you x squared minus 5x minus 36, and this does have an equal sign, so this is now an equation, it's not an expression. We've moved on to 5x, sorry, I got ahead of myself, not 5, 6, 5x, okay? So you have to have the 0 in here in order to use the zero product property. It has to be equal to something in order to use this. I can't just do this from an expression. So how are we going to factor this? So my very first thing I'm seeing is, it's a trinomial, so can I use the perfect square trinomial? Instinctively, I want to say yes, because my first term is squared. 36, I know, has a whole number square root, so it seems super convincing, like I'm gonna be able to do this. But if you kind of start working through using that perfect square trinomial, you will never get into this, you will never achieve that 2ab. It will never come up to 5x. Another hint to me was, well, I have subtraction and subtraction. That's not ever the case in a perfect square trinomial. You either have both addition or subtraction and addition. So since they're both subtraction, I know I'm not able to use the perfect square trinomial. So I have to think, what other ways do I know in order to factor trinomial? If you think back to the last video, how we factored them was we first started by finding all factors of 36. Okay, so we kind of start up on that list at the bottom at 1. That's one that we always like to use, is 1 and itself. Okay, so then we keep going from there. Oops, sorry. Right back. Okay, sorry about that. So we keep going up from there. Is 2 a factor? Yes, 2 is a factor. Would be 2 and 18. Say, okay, what else is factors? We start going up to 3. Is 36 divisible by 3? Yes, it'd be 3 and 12. Okay, keep going down this list. What else do we have? When we get to 4, that works. That would be 4 and 9. I think that's all I got in my head. You can keep going through this list. Those are the factors that I'm coming up with on the spot here. And I'm going to test some of these out. So the reason we find these factors is whatever 2 numbers we use in these binomials, right? I can already set these up. I know that's how the front of it's going to look. The 2 numbers that go here have to multiply to negative 36 and add to negative 5. Okay, so since these are going to be negative to negative 36, I know one of these factors has to be negative in order to achieve a negative 36. So how can I add to negative 5? 1 and 36, it's never going to get me there. 2 and 18, no matter which way I add, subtract anything, I'm not going to get down to negative 5. Same thing with 3 and 12. There's just not enough difference between them, right? I mean, there's too much really difference between them. I can't subtract or add down to negative 5. What about 4 and 9 though? Okay, so if I have a negative 4 plus positive 9, that gets me to positive 5. Okay, so what if I make this 9 negative? Then I have a negative 9 plus positive 4. That's going to get me to negative 5. What about negative 9 times positive 4? That also gets me to negative 36. Okay, so I've met both of the restrictions here. I've added to the middle and I've multiplied to the last term. So that tells me the 2 numbers I'm going to use is negative 4, or negative 9 and positive 4. But I'm not done here, right? Factoring was a step to get me what I needed to find. What I needed to find were the zeros of the function. So technically this factorization is still set equal to 0, right? I factored this part, I'm still set equal to 0. In order to find the zeros, you take each of these binomials and set each equal to 0 separately. So let's take x minus 9 equals 0, and then x plus 4 equals 0. If you solve for x in each of these equations, that's the zeros of the function. So I would have to add 9 over, so it'd be x equals 9. I'd have to subtract 4 over, so it would be x equals negative 4. So my zeros of the function, x equals positive 9 and negative 4. Okay. Okay, that is all for this time. Let me know if you have any questions. Oh, thank you.